Hello, cosmic explorers, and welcome back to our channel. Today, we're embarking on a journey to a world so extraordinary, so unbelievably opulent, it sounds like something straight out of a science fiction novel. We're talking about a planet where the very ground beneath your feet could be pure diamond, and the skies above might just rain rubies. Get ready to have your mind blown as we unveil the fascinating, lesser-known secrets of the diamond planet and the phenomenon of ruby rain. For centuries, the idea of planets made of precious gems was confined to myth and fantasy. But in the early 21st century, astronomers turned that fantasy into a staggering reality with the discovery of 55 Cancri e. Now, you might have heard this planet referred to as the Diamond Planet, and for good reason. It's an exoplanet orbiting its star, 55 Cancri A, in the constellation Cancer, about 40 light-years away from Earth. That's close enough for us to study it in remarkable detail, yet far enough to keep its true wonders shrouded in a bit of mystery. But what makes 55 Cancri E so special? It's not just a rocky world, it's a super-Earth, meaning it's significantly more massive than our home planet, weighing in at about 8 times Earth's mass, and roughly twice our radius. However, its proximity to its star is what truly sets it apart. 55 Cancri E orbits incredibly close, completing a full revolution in a mere 18 hours. Imagine a year lasting less than a single day on Earth. This extreme proximity means its surface temperatures are scorching, estimated to be around 2,700 degrees Celsius, or nearly 4,900 degrees Fahrenheit. Hot enough to melt rock, right? Well, yes, but that's where the diamond comes in. Early observations, particularly from the Spitzer Space Telescope, revealed something astonishing about 55 Cancri E's composition. Scientists theorized that due to its parent star being carbon-rich and the planet's high temperatures and immense internal pressures, a significant portion of its interior could be composed of carbon, not in its common rocky form, but in its crystalline, high-pressure phase, diamond. Imagine vast oceans of molten rock, with colossal diamond veins running through the planetary mantle, perhaps even forming the very crust. While it's unlikely to be a single, giant diamond ball floating in space, the term diamond planet is a bit of a simplification. The sheer scale of the potential diamond content is mind-boggling. Some estimates suggested that up to a third of the planet's mass could be diamond. That's trillions upon trillions of carats. Now, let's talk about something even more exotic, ruby rain. While the diamond aspect of 55 Cancri E is based on compositional models, the idea of ruby rain often comes from the study of other extreme exoplanets, like WASP 121b. This hot Jupiter is another example of an exoplanet with truly bizarre atmospheric conditions. WASP 121b is an ultra-hot gas giant that orbits its star so closely that its atmosphere is literally being ripped apart, with temperatures reaching over 2,500 degrees Celsius, 4,500 degrees Fahrenheit, on its dayside. So, how does ruby rain tie into this? The link isn't direct to 55 Cancri E, but rather to the broader understanding of exoplanetary atmospheric chemistry. In the extreme temperatures of planets like WASP 121b, elements that are gases on Earth can become solid, and vice versa. Spectroscopic analysis of some exoplanet atmospheres has detected the presence of exotic materials, including corundum, which is the mineral form of aluminium oxide. When corundum contains trace amounts of chromium, it forms ruby. If it contains titanium and iron, it forms sapphire. The theory is that on some ultra-hot exoplanets, where the atmospheric pressure and temperature are just right, and where the elemental composition includes aluminium and oxygen, these conditions could lead to the formation of corundum crystals. Imagine an atmosphere so hot that it vaporizes rock, then as these superheated gases rise and cool slightly, these crystalline forms could condense and fall as rain. While we haven't directly observed ruby rain on 55 Cancri e or any specific exoplanet yet, the potential for such phenomena exists within the realm of extreme exoplanetary conditions, where temperatures allow for the vaporization and recondensation of minerals. It's a tantalizing thought that illustrates just how diverse and mind-bogglingly strange other worlds can be. But how did we come to discover these incredible facts about 55 Cancri e? The story begins not with diamonds, but with the subtle wobble of a star. The first hint of 55 Cancri e's existence came in 2004, when a team of astronomers using the radial velocity method detected a tiny gravitational tug on its parent star, 55 Cancri a. This method works by observing the minute shifts in a star's light as it's pulled slightly towards and away from us by the gravity of an orbiting planet. These shifts cause a Doppler effect, making the star's light appear slightly bluer when moving towards us and redder when moving away. By precisely measuring these wobbles, astronomers can infer the presence and even the mass of unseen planets. For years, 55 Cancri a was known to host a system of multiple planets, making it one of the most populous exoplanetary systems discovered at the time. However, the precise nature of 55 Cancri e remained elusive. It was initially thought to be a gas giant, given its inferred mass. The real breakthrough came in 2011, when astronomers using the Spitzer Space Telescope and later the Hubble Space Telescope were able to observe 55 Cancri e transiting its star. A transit occurs when a planet passes directly in front of its star from our perspective, causing a tiny, measurable dip in the star's brightness. This observation was crucial because it allowed scientists to determine the planet's radius, something that radial velocity alone cannot do. Once they had both the mass, from radial velocity, and the radius, from transit data, astronomers could calculate the planet's density. And that's where the surprise came in. The calculated density of 55 Cancri e was far too high for a gas giant or even a typical rocky planet like Earth, which is largely composed of silicates, rock-forming minerals. Instead, its density suggested a composition rich in heavier elements, specifically carbon. This finding, published in a landmark paper, led to the revolutionary hypothesis: 55 Cancri e was a carbon-rich world, and a significant portion of that carbon was likely in the form of diamond and graphite. This theory was further supported by the high carbon-to-oxygen ratio of its parent star, suggesting that the building blocks for the planet itself were unusually carbon-rich. The discovery of 55 Cancri e's unique composition challenged long-held assumptions about planetary formation. It showed us that rocky planets aren't just made of the same stuff as Earth, Mars, or Venus. They can have wildly different chemistries depending on the environment in which they form. The diamond planet 55 Cancri e and the theoretical possibility of ruby rain on other extreme worlds remind us just how much more there is to discover beyond our solar system. These are not just scientific curiosities, they push the boundaries of our understanding of geology, chemistry, and the very processes that create planets. They spark our imagination and fuel our desire to explore the cosmos. What do you think about a planet made of diamonds? Or skies that rain rubies? Let us know in the comments below. If you enjoyed this cosmic deep dive, make sure to like this video and subscribe for more mind-bending journeys through the universe. Until next time, keep looking up,